Welcome to the Innovations in EDA webcast series. Today's topic is titled How to Design Power Electronics, High-Frequency Power Semiconductor Modeling. I'm Carmina, and I have a few short announcements before we begin. This webcast is designed to be interactive between you and our presenter. You can ask chat questions at any time. During the question and answer portion, our presenter will make every effort to answer your questions live, so I do apologize in advance if we don't get to yours. But don't worry, because if we do run out of time, our presenter will respond to the remaining questions via email. After our webcast, please fill out the short survey. By submitting this survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. I just wanted to mention about, on our next slide, Emily, Agilent's Electronic Measurement Group is now Keysight Technologies. Keysight Technologies Incorporated is the world's leading electronic measurement company, transforming today's measurement experience through innovation in wireless, modular, and software solutions. The company's 9,500 employees serve customers in more than 100 countries. Visit us at www.keysight.com for more information. Let's move on to today's presentation. It is my pleasure to introduce our presenter, Professor Ingmar Kalfas. Professor Kalfas received his degree in electrical engineering from the University of Stuttgart in 2000 and his doctorate in electrical engineering from the University of Ulm in 2005. His career in academia includes positions at National and University of Ireland, University of Ulm, and the Fraunhofer Institute. From 2009 to 2012, he was a professor at the Karlsruhe Institute of Technology. Since 2013, he has held the newly established chair for robust power semiconductor systems at the University of Stuttgart as part of the Robert Bosch Center for Power Electronics. Welcome, Professor Kalfas. You now have the floor.
Thank you, Carmina, and thank you, Keysight, for inviting me to present this webcast. Ladies and gentlemen, welcome to you, and thank you for your interest in this topic. In the upcoming 45 minutes, I would like to talk to you about the area of power electronic design, and I would like to show you how high-frequency aspects are playing an important role in power electronic modeling and design. Okay, I will first give you a quick outline of the talk. So after an introduction to semiconductor-based power electronics, I would like to point out some challenges in power module design. And then in the main part, I will highlight some aspects of power module design flow, covering the areas of modeling and characterization, and then talking about the need for electro-thermal co-simulations and their benefit. And I will then show you some recent examples of our work where we focus on the integration of power electronic circuits using gallium nitride as a wide bandgap semiconductor material. So let's move on to the introduction. First of all, it may not be so obvious where the world of microwaves and power electronics meet. They seem to be distinct areas, but it turns out they are not. First of all, the underlying technology is semiconductors, and when today we use semiconductors to operate at microwaves, millimeter waves, and even sub-millimeter wave frequencies, we also use semiconductors for power electronic circuits. They are on different edges of this frequency and power chart, and in the high frequency end, we have a competing compound semiconductors, gallium arsenide, indium phosphide based semiconductors, and they are today being challenged by ever faster silicon-based technologies, MOSFETs and silicon germanium HBTs. Now, in the area of power electronics, the situation is somewhat opposite. We have the conventional silicon-based power devices, which are mainly IGBTs and MOSFETs, and they are today challenged by compound semiconductors, wideband semiconductors, which are silicon carbide MOSFETs and IGBTs, and more recently also gallium nitride high electron mobility transistors. Now in both areas, these different semiconductor technologies compete in terms of performance, in terms of maturity and reliability. Of course, cost is a vital issue in terms of applications, and all semiconductors try to achieve a good market share and try to define applications. The same semiconductors can be scaled and engineered to enter these two areas of high frequencies of power electronics. And a very interesting example is gallium nitride as a wide bandgap semiconductor material. Gallium nitride has originated as a technology for RF power amplifiers in the medium to low microwave area, and gallium nitride has recently evolved in both areas, so we can tailor gallium nitride to enter the high millimeter wave area where they provide very good power amplifiers, and also you can tailor gallium nitride to enter the area of power electronics, where it's about switch mode converter designs with several hundreds and thousand volts of blocking voltage. Okay, when I talk about power electronics, what do I mean? I like to show this definition, which is from a UK strategy paper, which says that power electronics is the extension of solid-state electronics away from the handling of communications, data, and signal into the business of efficiently handling power. And here comes the very first, the first important aspect is that power electronics covers power ranges from milliwatts to gigawatts. So it's a really, it's an extreme wide spectrum which is referred to as power electronics. And one always has to specify actually which power range is addressed. The same source goes on to say that power electronics is an enabling technology which often determines a performance and competitive advantage of a complete system. Even if power electronics is not a final system, such as an electronically driven car or a mobile phone or computer, it may be a decisive element which decides on the competitive advantage of such a system. Therefore, it is true to say that the importance of power electronics to the economy is very much greater than the direct market value it represents. Power electronics is typically not seen as an end product, but it plays a critical role in very important aspects ranging from our energy production, transformation, and so on, into the area of mobility and so on. Okay, the next slide shows a graph which depicts some of the applications and technologies in a chart which has the switching frequency on the x-axis and the power range on the y-axis. There are many different of these charts around, and typically different semiconductor manufacturers will present them in different ways. I have here chosen a graph from the French CEA Leti lab, which I like very much, which shows you that silicon-based components are today being challenged by the two wide bandgap semiconductors, gallium nitride and silicon carbide, where silicon carbide is dedicated to extremely high power conversion for energy systems. Silicon carbide operates at blocking voltages way beyond 1 kilovolt and can achieve very high switching current. Due to relatively high cost, it will therefore address niche markets of extremely high power. Gallium nitride, on the other hand, is able to operate at very high switching frequencies, and we will discuss the implications of this later on. And gallium nitride is entering essentially the same markets where today's silicon components are playing a major role. Gallium nitride is today operating at blocking voltages below 1 kilovolt, but achieves around up to 100 ampere switching current. Since it can be fabricated on cheap silicon substrates, this material can also address mass markets. Okay, so how to benchmark and how to classify and judge the suitability of different power semiconductors for applications? We all know the Johnson figure of merit, which is a figure which describes the capability of handling power at high frequencies. We can classify the semiconductors according to this figure of merit. There's also the Baliga figure of merit, which describes the capability of minimizing the on-state power loss when you operate the transistor as a switch. And in this table here, we see the four dominant semiconductor families, silicon, gallium arsenide, and then the wide bandgaps silicon carbide and gallium nitride, where one can show that Johnson and Baliga figures of merit are extremely high for the compound semiconductors as opposed to silicon. Another very important figure of merit can be derived from the calculation of switching loss. Here you see a simplified representation of switching loss in a power converter. It is here written as a function of transistor area, and in the simplified version you see that there is a term which is related to the on-state loss when the switch transistor is conducting, and a second term which is related to switching loss and which is proportional to the switching frequency f. Now, when one can show that this function has a minimum at an optimum transistor area, and the minimum obtainable switching loss can be written here in the second equation, and we can distinguish a product of two terms, where the first term relates to the operation of the switching converter. So here we find the switch current, the blocking voltage, the switching frequency, and the gate charging current. And there is the second term which contains the semiconductor-related entities, namely the on resistance of the switch transistor and the total switching charge, which needs to be charged and decharged from the transistor gate when operating as a switch. This total switching charge is also often related to the gate charge, and this product of on resistance and gate charge is now a figure of merit for operating a semiconductor as in a switching converter. It is important to say that a smaller product is a better figure of merit, and we can now classify the three major power semiconductor families in this chart here, which shows the figure of merit as a function of the breakdown voltage or blocking voltage of these devices. We see the blue dots, which are sample examples of power semiconductors, which relate to gallium nitride, the red for silicon carbide and the green for silicon. Now it is interesting to point out that silicon power devices achieve blocking voltages up to about 1 kilovolt. 600 volt is a very popular voltage class, and it is also interesting to note that silicon power devices are actually outperforming their intrinsic technology limit, which is based on theoretical calculations factoring in mobility and so on of silicon. And this shows that silicon power devices are extremely mature. It also for silicon carbide, we see that silicon carbide transistors achieve extremely high blocking voltages, well beyond 1 kilovolts, which is not achieved by the other transistor families, and it gets close to its own material limit. The situation is somewhat different for gallium nitride, which intrinsically has the best figure of merit in terms of R1 times QG. So in principle, in theory, it outperforms both silicon and silicon carbide for this figure of merit. But in practice today, gallium nitride power transistors are not yet achieving their intrinsic limit for this figure of merit. And in terms of the breakdown voltages, they range in the same area as silicon devices. Okay, challenges in power module design. So when we want to design a power converter, whether it's a DC-DC converter or DC-AC or AC-DC converter, we want it to be small and light and of course cheap, but at the same time it needs to be efficient. We want to minimize the loss power in the switch, and it needs to be robust. It needs to have very high lifetime, and at the same time it needs to be electromagnetically compatible to the other electronics operated in a system. Think of a car, for instance. So the problem we are faced is to maximize the product of converter efficiency and power density under the frame conditions of keeping a robust, high lifetime converter which is EMC well behaved. That is the basic problem, the challenge in designing a converter. These challenges have also been formulated and quantified by the European Center for Power Electronics, ECPE, a very important European council in that area, which has formulated a technology roadmap and claiming goals to be achieved around 2020, where it's about an increase of the power density by a factor of 2 to 3 compared to today's converters. The power to mass ratio, which translates into weight, should be increased by a factor of 2, and so on. Efficiency has to be improved, and here, to read this correctly, the improvement by a factor of 3 is related to the loss power, which should be reduced by a factor of 3. All this should go along with the reduction of cost, and we need to improve the robustness of these power electronics. Now, the problem with these goals is that they are somewhat, they cannot be met at the same time in every case. So generally speaking, a power converter consists of power switches, which in today's talk we concentrate on transistor switches. They are surrounded by passive elements, which are input, output filters, and the entire converter is surrounded by control electronics. Now, if we want to reduce the size and the weight, we see that for at least for converters which are operating in a power class of some kilowatts and in voltage classes of several hundred volts, the size and weight of these converters is typically defined by the passive components in the filters. To reduce these elements, the measure which is being adopted is to increase the switching frequency, because both coils, inductors, and capacitors in these filters scale proportionally to, inversely proportionally to the switching frequency. The problem when increasing the switching frequency is that at the same time we increase the switching loss, which at least these components which are proportional to the switching frequency itself. So, so here is again written the equation for switching loss with the static term and the terms related to the switching loss, where here is also included the fact that also at the output the transistor needs to be charged and decharged. In order to counteract the effect of higher switching frequency, we need devices with a smaller figure of merit of R1 times QSW, the switching charge. A second measure, which you can see from the second term here, where the switching loss also scales inversely proportional to the charging current, which translates into the slew rate of charging and decharging such a power transistor. Here we need to adopt high slew rates, so high D to DT slopes, in order to minimize the switching loss. Another problem in the design of power converters is parasitic LC resonances, which originate due to layout issues and the geometrical extension of such converters, both in the gate and in the power loops. These resonances need to be minimized and controlled through a very compact layout, and which results in the need for high integration density. Another problem for reducing size and weight of such converters is that you typically have to spend a lot of effort in cooling such converters, because they produce a significant amount of loss power, which translates into heat. This cooling effort limits size, weight, and cost of these converters, and therefore wide bandgap semiconductors, which offer a low intrinsic carrier density and therefore a potential high temperature operation, are of major interest. Another big issue in power converter design is electromagnetic compatibility, which typically needs to be met and achieved by additional shielding and filtering used in these converters, which again limit the cost, size, and weight. Increasing the D to DT slopes in these switching converters translates into higher cutoff frequencies in the output spectrum of such converters. Therefore, it becomes necessary to adopt an EMC-oriented design approach and to control the high-frequency components in such converters. Such switching slopes, just to give you some numbers, at least for gallium nitride-based switches, can lie in the order of only a few nanoseconds, and therefore we are actually entering the area of gigahertz in terms of the frequency spectrum. Okay, this chart tries to show that meeting these individual goals with the discussed design measures, some design measure will bring an improvement in some design goals, but it will actually bring a disadvantage in other areas. So the example of the switching frequency obviously reduces size and weight. It will also have an impact on reducing the cost, but at the same time, if we do not do anything else, we will reduce the efficiency of such converters. It will also affect EMC and robustness negatively. To counteract this, we need to increase the D to DT slopes, but that will have, again, a negative effect on EMC, and so on. It is therefore required to have an optimum, for an optimum design, to refine the design flow of power converters in terms of RF, and this needs to be done from device characterization to the area of modeling and to the actual circuit design and analysis. Okay, one therefore has to control the entire design chain, going from characterization of the power semiconductor to its modeling and to the design. In characterization, it is obvious that one needs to control the IV and characterize IV characteristics, capacitance voltage characteristics, and charge voltage characteristics. But in term for power electronics, it is vitally important to also understand and characterize the respective temperature dependencies. Also, especially for gallium nitride, there is a big issue of low frequency dispersion effects, which are dynamic effects, and therefore dynamic characterization is an important issue. In terms of modeling, one not only needs to model the static performance of these devices, but also with an increasing importance, the dynamics of these power transistors become important. One also needs to have a thermal model, because temperature will of course impact current in the devices, and both temperature and current are interrelated. In the design world, one has to link both time and frequency domain analysis in the electrical domain to a coupled simulation controlling the electromagnetic effects and also the thermal effects. Okay, that brings me to the topic of modeling and characterization, which I would like to introduce by considering the fact that a transistor, when you operate it as a switch, can be described either as a very simple switch, which is of course too simple description of a transistor, because we know that a physical device, a transistor, is really a highly complex nonlinear device. So here is shown an example of a high electron mobility transistor equivalent circuit, which has very complex entities. Now, the challenge for the designer is to decide on the required complexity of the model and the required fidelity. We often encounter models which are relatively simple, describing on resistance, capacitances, describing drain currents, transconductance of the device, maybe also some including some diodes which are present, for instance, in the gate of a high electron mobility transistor or in the bulk of a MOSFET. One then goes on to describe the voltage dependence of these entities, but often these voltage dependencies are described in a one-dimensional way, which is physically not true, because all charges and currents in a transistor are at least two-dimensional functions of the external control voltages. Going from there, these devices show non-quasi-static and low-frequency dispersion effects, which should be included in the model as well. In parallel, we need to define electro-thermal models, and the packaging parasitics should also be included in such a in order to come up with a high fidelity model. Now, to show you one example of challenging modeling, I would like to consider the dynamic IV when one is switching a typical inductive load. You see here the transitions in the output characteristic of such a switch transistor when it is switching an inductive load. Here we see the switching waveforms associated with this transition, and from when we want to calculate the efficiency, we need to calculate the switching loss, which is the product of current and voltage, of course, and which can be approximated by such a triangular function during the switching, the switch on and switch on transition. And this results into this equation, which says that the switching power is a function of the total switched charge and the switching, the charging current and the switching frequency. So if you want to calculate the switching loss, we need to know the gate charge of such a switching transistor. Now, this behavior can also be nicely shown in a circuit simulator. We are actually using ADS, which is of course more typically known from the RF world as a very powerful RF design environment. we adopt this for the design of power electronic circuits, and you can show for such an example of switching an inductive load the dynamic IV characteristic of such a transistor, which actually transits from the subthreshold region when the transistor is blocking through the saturation region. So here we have the current commutation, what is called the current commutation, when the current is rising under nearly constant voltage characteristics. And then in the second phase, the voltage, the drain voltage is dropping down to the minimum voltage, which is due to the on resistance. So it is actually a quite complex transition which the transistor undergoes. And to describe this in the model, the first approach would be to have a look at the data sheet of such power transistors, where you can look at the input, output, and reverse capacitance. Here you see a measurement which is taken under typical data sheet defined conditions, which are actually operating the transistor in subthreshold operations. So here at 0 volt gate bias for a blocking, for a normally off or enhancement mode device, and one is then sweeping the drain source voltage at a particular frequency. So when we derive, when we want to calculate the charge in order to calculate the switching loss, we could derive it from these capacitance characteristic by the known relation of charge and capacitance. So we would integrate here capacitance versus voltage to derive the charge. Now this would lead to a calculation error, which I try to highlight here. These two graphs show the gate source and the gate drain capacitance. In this example here for a gallium arsenide power hemmed, but qualitatively speaking, this is true also for power transistors. And we see that the capacitance is a strong two-dimensional nonlinear function of the both of the two control voltages. Now, if we look at a transition of a switch and we consider the condition which considers capacitance in the data sheet, the transition would go from a high blocking voltage and at subthreshold to a low drain voltage. The real transition of the transistor actually goes along the black path, which goes into, during current commutation, into the saturated region of the transistor performance, and then the voltage drops for conducting conditions. So obviously it would be a dramatic error to estimate the charge just from capacitance taken through the data sheet definition. It is therefore better to derive capacitance from actual charge measurements. Here this graph shows the measurement of the gate charge as a function of the gate source voltage. We can identify the characteristic Miller plateau, which is due to the Miller capacitance in this device. And we can now, from this charge measurement, derive capacitance by essentially looking at the slopes of these curves. So for modeling a transistor, it is important to get the correct capacitance value, and it is better to derive it from a charge measurement. Okay. Moving on to low frequency dispersion effects, I'll try to speed up a little now. We know very well from the RF world that gallium nitride has a lot of, or used to have a lot of issues due to trapping effects which occur at interfaces at several locations inside these devices. In the RF world, this is called drain lag and gate lag, and leads to low frequency dispersion effects. And the same physical effects of trapping lead in the area of power electronics to the so-called dynamic RON, which means that during or after, shortly after an off to on switching transition, the on resistance remains very high over a certain period of time, which is associated with the trapping time constants, which can range from there are some very fast traps on the order of nanoseconds, but there are also deep traps with high time constants on the order of milliseconds, which degrade the on resistance of these devices. Now, this can also be done, measured during characterization. This is shown on this slide here, where we see the control voltages. The device is stressed at a high voltage, and then the device is opened up, and one measures the drain current after a certain total delay time, and we can then derive. We can show the measurement then for different stress voltages is shown on this slide. So here the stress voltage goes from 200 volts down to 50 volts, and we see that obviously the trapping states in the off state affect the on resistance in the on state. So for a higher stress voltage, the on resistance becomes larger than for a low stress voltage. Looking at the on resistance versus time, one is limited, of course, in the slew rate of the power supplies. Also, one needs to introduce some delays before the measurement occurs in order to have stable voltages conditions. But here is shown the on resistance time dependence on a chart which starts at around 2.5 microseconds, and here we can identify that the on resistance actually drops with time, which is associated to time constants of the traps. Now the important question is, how do these devices behave on the order of nanoseconds, tens or hundreds of nanoseconds, which is where we would like to have the actual slew rates of the switch. For this, one needs to have very fast dynamic pulses. It is interesting to do these measurements on different devices. Here you see the measurement of 3 different gallium nitride power devices, all comparable voltage classes, actually 600 volt blocking voltages, and we see that there is a strong difference in these devices. Some show very good and low on resistance, and some show higher on resistance. Okay, the on resistance has also a very strong dependence on temperature, which leads to the fact that one also needs to include a temperature model in the transistor model itself. And it is, of course, very obvious that the on resistance, which is related to the mobility of the charge carriers in the channel, the on resistance is increasing with increasing operating temperature of these devices. This measurement here relates to a silicon carbide MOSFET with 600 volts blocking voltages. So to sum up here, the model requirements are that one needs to adopt a 2-dimensional capacitance model for gate source and gate drain capacitance. We need to worry about low frequency dispersion effects and need to include this in our models, and a thermal model is also required. Okay, I would like to show you some aspects of electro-thermal co-simulation on the example of such a power module, which is an integrated half and full bridge, so 2 switch transistors and 4 switching transistors. This was realized with bare die silicon carbide MOSFETs, driver ICs, bootstrap supply diodes, and buffer capacitors on a single aluminum nitride direct bonded copper substrate. This is designed for a switching frequency of 100 kilohertz and a power capability of up to 10 kilowatts. Now, when we design such a board, we are able to do a co-simulation of the electrical entities, current and voltage and electrical power. We co-simulated with the temperature transient of such a device, and this co-simulation can also be done in ADS. We operate here this Fullbridge module as a DC to AC inverter. So we have an AC output where we see the output voltage, output current, and the product becoming the output power. And we can now see how the temperature in our 4 switching transistors of the Fullbridge reacts to this output power. Okay, this can be shown here in a thermal plot of the 4 switching transistors. What one can observe here is that, for instance, that the temperature of the silicon carbide MOSFET pulsates with the 60 Hertz output frequency of the AC grid. We are also able to say that the current and voltage which is switched in these transistors results in a temperature difference of about 5 degrees centigrade. And we see that the temperature peaking is only visible in the junction layer of the switching FETs and is not affecting the surrounding area of this power module, which indicates that the thermal time constants of the involved materials are high enough such that the temperature is not spread away from the switching transistors. Such an electro-thermal co-simulation gives important new degrees of freedom. We can use this for extracting thermal equivalent circuits, and of course one can now start to optimize to obtain a very compact layout of such modules. It can be then in the conventional hybrid power modules or the multi-chip module, which was shown earlier on, and the same approach can be used for on-chip thermal control of the temperature distribution. It allows for reduction of safety margins. It can ultimately lead to a robustness-oriented design and to lifetime prediction of such power modules. Okay, finally, gallium nitride integration. Just to introduce very quickly the advantages and disadvantages of gallium nitride. We have already seen that the gallium nitride can be tailored both for power electronics and for microwave applications. It shows intrinsically the best figure of merit, Ron times QG, better than silicon and silicon carbide. It is very cost efficient when it is processed on silicon substrates, and a very important feature is that these gallium nitride transistors are almost exclusively lateral devices, which are therefore amenable to monolithic functional integration, where you can integrate several components in addition to the power switch. The drawbacks today are that this material is less mature. There are a lot of issues which are related to traps, leading to dynamic iron. Another problem is that intrinsically such transistors are depletion mode or normally on devices, which is a problem for power electronics. It is possible to do this as normally off devices, but that involves more complex processing, such as p-doping of the gate, or the combination of a blocking silicon transistor with a gallium nitride transistor, which is then commonly referred to as a cascode arrangement. Okay, to sum up this talk, I would like to show you an example of how one can integrate, increase the functional integration density using gallium nitride. A conventional hybrid assembly of a switching transistor and a driver and some additional passives would lead for a normally on device into the prohibitive shoot through currents in case the driver fails. And it leads, due to the resonance frequencies, to overshoot voltages and to oscillations. We therefore tried to increase the robustness by coming up with a normally off default behavior, and to allow to increase the switching speed by reducing the gate loop inductances. and this can be done ultimately by monolithic integration of this power transistor. Okay, here it's shown how this can be done. This is an example which was a collaboration with the Fraunhofer Institute in Germany, which does these gallium nitride transistors. They are normally on devices, but by introducing diodes monolithically with the power transistor, one can obtain a default normally off behavior. And this transistor can be used as a driver stage to control the power transistor. This normally quasi-normally off transistor is used as the pull-up driver stage in conjunction with a pull-down driver stage, and this final driver stage is then integrated with the actual gallium nitride power transistor. The advantages are that we do not see any shoot-through current, and that we have a default pull-down behavior of the power FET using this driver circuit. Now, this arrangement of a gallium nitride driver stage and a gallium nitride power transistor was verified in a hybrid integration and finally in monolithic integration. Now, this picture shows the hybrid integration. The bottom part, you see the power switch transistor, which is gallium nitride based, and then gallium nitride transistors used as the pull-up and pull-down driver stages, and then there is also a gallium nitride based diode, and with this one can realize a complete a boost converter, which is shown on the top photograph, and the operation of this hybrid integrated gallium nitride driver and power transistor is shown here. The switching transistors during turn on and turn off turned out to be very fast. During turn on, we do not see any overshoots. There are no oscillations, and we obtain very fast switching with a rise time of about 5 nanoseconds and a slew rate of about 90 volts per nanosecond. Turn-off transition is also very fast with about 1 nanosecond fall time and a D to DT slew rate of close to 200 volts per nanosecond. And final slide shows you a complete monolithic integration of this driver stage, which is a pull-up and pull-down transistor, where the pull-up transistor has a normally off default behavior. This driver stage is monolithically integrated with the power transistor. The bottom part, you see the chip photograph. This is again a technology of Fraunhofer IAF, and with this monolithic integration, we have close to complete elimination of the parasitic gate loop inductance, and we are combining in a monolithic way transistors with different voltage ratings. The power transistor is designed for 600 volt blocking voltage, and it is dimensioned for 24 ampere. This is this big transistor on the right part, and the driver stages are using transistors with blocking voltages less than 100 volts and currents of 2 and 1 amperes. Okay, that brings me to the end of this webcast, and I would like to conclude by showing you this picture, which brings me back to the start of the webcast, where I tried to show you that the areas of microwaves and power electronics have a lot of commonalities, and in my opinion, both areas are building on the same roots. Both areas are building on the semiconductors, and the devices build on these semiconductors. In both areas, we need a good understanding of the semiconductors. We need to model them accurately. We have the identical or very similar design approaches in both areas, controlling RF effects, and the simulation techniques are similar, even if we are building two very different trees, either high power switch mode converters or the area of microwave front ends. And of course, in both areas, we are competing in order to improve or to meet the application requirements. In both areas, the issue is about reducing the cost, obtaining more market share, and bringing innovations in order to bring new applications about. And with this slide, I thank you very much for your attention. Brings me to the end of this webcast, and we will now be answering the questions which you may have formulated during my talk. Thank you very much for your attention.
Thank you so much, Professor Kalfas. And that's right, we will start our questions. Remember, folks, we don't get to all of yours. We will respond to the remaining questions via email. I also have Dr. Colin Warwick, the Power Electronics Product Manager, who's joining us for the question and answer session. Welcome, Colin.
Thank you, Carmina. Yes, I'll read out the questions for you, Professor Kalfas, that have come in. We don't have time for them all, but if your question isn't answered live, we will follow up with an email. So, first question is from Lee. It says, can you please explain how to model the trap effects, if that's possible, Professor Kalfas? Anyway, to model traps, tricky thing to do.
Yes. Yes, of course. It is difficult to answer quickly, but there are several ways to model trapping effects. On the slide, I have just shown one typical way of combining actually two drain source current sources in such a device, where at DC only one of these drain source current sources is active, and at AC, because it's combined with an RC network, the second source is entering as well, and therefore the overall current will be the sum of the two current sources. And with such an equivalent circuit representation, you can achieve a different behavior under DC and AC characteristics. This can be even extended to several, to more current sources, and one has a degree of freedom of defining the transition frequency, or actually the associated time constant. That's just one way of modeling such dispersion effects. And actually, from the world of RF devices, there are a lot of groups who have worked on the modeling of what is called their low-frequency dispersion effects, trapping effects, thermal effects. Even impact ionization has an associated time constant, and there are a number of different model approaches around.
Very good, thank you. Next question is from Amol. Can you talk about modeling a AlGaN/GaN, aluminum gallium nitride, gallium nitride, high electromobility transistor, particularly with regard to fast convergence? I guess convergence is on everybody's minds with these models.
Yes, okay. I can try to give you a quick point of view from my side. First of all, I think it's important to say that there is no, at least to my knowledge, there is no standard model which would be commonly adopted by the community to describe an AlGaN/GaN power hemmed transistor. So if you look at these different manufacturers of such power devices, they will actually use a large variety of models. And these models typically are relatively simple models coming out of the RF world. So we know from the RF world we have many very complex models which describe the gallium nitride transistor and its RF behavior. And what can be done is to try and adopt these models from the RF world and to extract the parameters for a power transistor. There is no standard model for this, and there is a large degree of freedom in the model complexity which you adopt. Another issue which is very important in power electronics is that the model also needs to be very robust and stable for the simulator to converge, because when you operate such a transistor as in a switching converter, it actually transits through very extreme states, from blocking of very high voltages through the saturation regime to the conduction of very high currents, and this poses very stringent demands on model convergence.
Yeah, thank you. That's very good. So next question is from Surab, I think that's pronounced. Its silicon insulated gate bipolar transistor datasheets often contain E on-off and RR data. Could such data be published for GaN MOSFETs? To what degree could it be trusted for a new design?
Okay, can you just repeat, sorry, the question? E on, what kind of data is in this data sheet? I'm
not sure what the acronym means. The acronym is EON/OFF, so that's me, E on-off, and then RR data. I don't know what the acronym means. Sorry.
Okay. I guess it's related.
Oh, here we are. It's turn on energy loss, turn off energy loss, and reverse recovery loss. Thank you.
And reverse recovery loss. Yes. Yes. Okay. The reverse recovery loss is related to the freewheeling diodes, which can either be standalone diodes or can be the intrinsic diodes, for instance, in MOSFETs. Therefore, you will also find this as a part of a transistor datasheet. Now, the gallium nitride transistor does not have a body diode, and it therefore cannot be used as a freewheeling diode, and it therefore you will also not be able to pinpoint a figure on reverse recovery of a gallium nitride HEMT transistor. But of course, the turn on and turn off losses occur also in the gallium nitride transistors, where one has to specify the frame conditions of the switching transition. But these are also figures which will be in the gallium nitride transistor datasheet.
Great. Thank you. That's all the time we have for questions. We'll follow up the questions we didn't get to in an email. And back to Carmina, who's going to wrap us up. Is that right, Carmina?
Oh, yes, but I wanted to ask Professor Kaufhaus, any closing comments to our audience as we wrap up?
Yeah.
Okay, yes. So here's my final slide. The wrap-up comment is that I thank you for attending this webcast. It is maybe a bit of a special topic to approach the area of power electronics from a high-frequency aspect, but I hope at least that with this webcast I was able to show you that high-frequency aspects are actually playing a very important role in the area of power electronic design, where switching frequencies are increasing and slew rates are increasing, and we need to adopt similar approaches in the design and in the modeling, which we can adopt from the RF world. So thank you for attending this webcast, is my final comment.
Thank you so much, Professor Kalfas. It's been our pleasure to spend this time with you this morning and afternoon for our folks. So thank you again. As we wrap up today's presentation, remember that we will email the links to the slides and the link to the on-demand version of this webcast. If you're viewing the on-demand version of this webcast and have a question about any material, you can email our presenter directly or email ourselves as well. I'd also like to remind the on-demand viewers to fill out the post-event survey. You're also invited to watch our next webcast, which is on October 8th, How to Design Broadband Impedance Matching Networks. Thank you again for attending today's webcast, How to Design Power Electronics, High-Frequency Power Semiconductor Modeling, brought to you by Keysight, ESOP, EDA. The copyright of the presentation materials is done by Keysight Technologies. For a current schedule of live and on-demand events, please visit us at www.keysight.com/find/events. I'm Carmina. Thank you so much for joining us, and have a great day.